So we find ourselves in a situation where we have what we call a cyclotron. Now, before we do this, I want to write a single equation off to the side here. And the single equation goes like this. F is equal to Q V B times sine theta. Just a reminder that the force we're talking about here is the motion force that's applied to a charge as it flies at a velocity through a magnetic field. Okay? So we've got a charge that's flying, through a magnetic field. Well, where's this magnetic field going to come from? I got a great big hockey puck shaped magnet on the ceiling where that magnet has a north-south polarity. And it's probably an electromagnet, so I can turn it on and off. Then I also have a great big hockey puck shaped magnet on the floor. We'll have it, north on the bottom, south on the top. Now, because that's the case, there's going to be a magnetic field between the ceiling and the floor. Now, I'm going to be kind of strategic about this, and I'm going to do it with my red marker. I'm going to say that descending from the ceiling all the way to the floor would be a magnetic field oriented downwards. Now, I happen to have a particle that's in the foreground. You can tell that it's in the foreground because there's a shadow. That dark spot is like a shadow for that particle. You see what I'm talking about? It's on the front edge of the lower hockey puck. It's hard to express things in 3 dimensions, so I want to make sure that everybody knows what I'm saying here, okay? Then in the background, there'd be a magnetic field that would be oriented downwards. And some people that have a hard time thinking in 3D, you can see why I would have a template already made up for us like this, because a lot of us would struggle to draw this in 3 dimensions convincingly, right? Off to the side, magnetic fields there over as well. Oriented. Well, I guess I don't have to write the B again. Oriented downwards. And then off to the other side. Now, each of these particles finds themselves in the magnetic field. But I just want to start off with this particle that's in the foreground. This particle that's in the foreground is going to be in motion. Okay? And so we're going to say, hey, this particle gets shot into this field like this. And as it gets shot into this field, it has a velocity. And so I want to, about midway down the page, I'm going to write that V value is the velocity of the charge. I'm also going to write that there's a Q. That's the charge that's in motion. And so Q is the charge magnitude. Charge magnitude. Obviously measured in coulombs, right? I'm going to add to this list on the right in a few minutes, but I want to keep on going. Anyway, if this charge is moving to the right and it's in the presence of a magnetic field that's pointed downwards, pull your right hand out for a minute. What direction is this charge going to get forced? Remember, magnetic field oriented downwards, so point your fingers down. And the velocity is to the right. So you're going to have to contort your hand a little bit to do this. I see some people doing a little bit of a twister maneuver there. That's cool. What direction is this charge going to get pushed? Yeah? Yeah, into the page. And so I'm going to represent this. I've already got 2 vectors on the go. A magnetic field vector, a velocity vector, and I'm going to try and make this be into the page kind of by doing it at an angle like this. I'm going to say that that's the direction of the force. Yes?
What does that 1 represent on the 4th line?
Right here? Arrow. This one here is the beginning of me writing a B. It's a typo. I'm sorry. Didn't mean to put it there. Sorry.
Is it true?
Oh, thank you so much. Let's make this be a positive charge, okay? That's how we can use the right-hand rule. You're absolutely right. Yes. If it was a negative charge, it would be going the other direction. Yeah. Okay. So it's getting pushed towards the center. Now, if it's getting pushed towards the center, can I just propose that this is a centripetal force? Because it seems to me that as it goes around this curve of the hockey puck, it's going to always be forced towards the center. But I'm having a hard time thinking three-dimensionally about that. Okay? So what I want to propose is, let's see what happens when it gets over here. When it gets over here, if this truly is a centripetal force, let's see what happens. Now we have to say we've got a velocity going into the page away from us. We'd have a magnetic field that's orienting downwards. Notice it's in the downward pointing magnetic field. Again, pull out your right hand, force your thumb into the page, magnetic field down. Oh, contorting my hand. Can you guys see that the palm is going to push towards the center of the gap, towards the center of the hockey puck? Make sure that you can do it with your hand and play that game of Twister. But it seems to me that that force is going to be towards the center of the scenario. I'm having a hard time getting back in here, but let's just, I'll squeeze it in. I got a V going there. Magnetic field going down. Can you guys get your right hands out? Give yourself some pattern support. Isn't the force going to be out of the page, but again, towards the center of the hockey puck scenario? And then when I get over to this far side, if the velocity was out of the page, again, use your right hand. What direction is the force going to be? Did I get confirmation? Is it towards the center again? Right, towards the center. So we got a force, we got a speed, or a velocity, I should say. And so I think this is pretty good support in terms of pattern recognition, that centripetal force is equal to the magnetic force, so QVB sine theta. Where are we getting our centripetal force from? QVB sine theta. Now, the sine theta, notice that I have this velocity firing in horizontally, and the magnetic field is vertical. So they're at right angles to each other. So what's sine of 90? In at 1? Okay, so if I let theta be 1, or theta be 90, that eliminates down to a 1. For a cyclotron, that's typically what we'd like to have. So we would say, and I'll pop back over to the left-hand side because I got to do a little bit of thinking now. I want to say, if I let theta equal 90 degrees, FB equals just QVB, right? Because the sine theta reduces down to just being equal to 1. I call that my equation 1. If I acknowledge that FB is equal to a centripetal force, and I know that centripetal force from our dynamics unit is mv squared over r, then that means that I could let equation 1 equal equation 2. And if I allow equation 1 to equal equation 2, I would be saying QVB equals mv squared over r. Now for a cyclotron, what I could do is I could use it. I could look at Q all by itself, and I could say, oh, okay, mv squared over velocity times magnetic field times r. And people are like, wait a minute, the v in the numerator and the v in the denominator, those are both speed. It's not like one's electrical potential or something like that. So that means that guy's going to eliminate, and I end up getting Q equals mv over br. And really, I only care about the magnitude of the v and the b, even though I've put an arrow hat over top of them. So if you like, you can put absolute values around all of this. But I suppose I should define that r. We're saying that r is the observed radius of curvature for the path. Now, things that we didn't really put in writing, but you guys called me out for, is that this illustration shows a positive charge. In a cyclotron. A negative charge would be forced to orbit the other direction. And earlier, I showed you folks an image of some charged particles that were being forced off to curl in one direction versus the other direction. I've got a small snapshot of it in the bottom right-hand corner here. But the idea is, and here, let me zoom in on this. If I were to have, I don't know if I can focus that close. If I were to have a radiative source of charged particles coming from this initial point here, and they were to be forced through a magnetic field, the negative charges would be forced to orbit one direction. The positive charges would be forced to orbit the other direction, right? Now, those orbits would have a radius, an initial radius of curvature, because, maybe the orbit's going to die out as it loses energy and energy dissipates. But I'd look at the initial radius of curvature. And if I could look at that original radius of curvature, if I knew how strong my magnetic field was, I could measure the radius of curvature, know my magnetic field. I might have some hypothesis about what particles are actually being radiated, knowing something about the nature of things. And I could figure out how fast they're being shot out. Or maybe I would know how fast they're being shot out, and I could figure out what the mass of the particles are and discern which particles are actually being shot out of my radiation source. And so this would be a tool for us to examine evidence like this and investigate what particles, how fast, what charge is being fired out of a radiation chamber. Anybody have any questions about that one? Yeah. Yeah, so how would if I look at this guy here and I say, oh, this is absolute values, well, the radius of curvature for this circular spin-off is going to be fine, an absolute value, but it's going to spin one way if it's negative, and it's going to spin the other way if it's positive charge, right? So even though this expression might be an absolute value, there's a left-handedness and a right-handedness to the scenario, right? There's this other thing, though. People say, well, you really cooked this. You cooked this. You said the initial velocity was perfectly horizontal. What would happen if somebody shot it at an angle? Well, wouldn't I have same hockey pucks, right? You don't have to draw this if you don't want to, but same hockey pucks. If I shot this thing at an angle, magnetic field would still be downwards. But if I fired it at an angle, it's going to be hard to believe in this as a 3D representation unless I talk it out. Doesn't that mean that the particle wouldn't go in a circle, but it would actually travel in like a corkscrew until it smashed into the floor? Because it would have an up-down component to its motion, not just a horizontal component to its motion. So yeah, if you fired it in at an angle, you get kind of a neat corkscrew effect. And again, there used to be a nice demonstration of this. You could play around with a cyclotron with a glowing gas chamber inside of it, and you could rotate the cyclotron or rotate the source, and you could make either a circle that glows or you could make a corkscrew that glows. Sadly, the Science Center was defunded. Bomb, bomb, bomb. Refund the Science Center. All right, anyway. Or travel to the places where they do have funded science centers, and you might be able to play around with this. I don't have this equipment, though, okay? So this is just like conversation for us. Sadly, can't do the demo on this one. But does it make sense to people? The corkscrew thing, I think, is really cool because it glows. And I know there's a private school around here that does own one of these things. I feel like we should go on a field trip or something, or say, hey, could we borrow that? But nothing so far.